All right, so today we're going to look at some properties with tangents. Okay, so we're looking at circles again, properties with tangents. So if you remember, a tangent is a line that intersects a circle in exactly one spot. Right? It intersects in exactly one spot. So we're going to look at some properties that happen when you have tangents and other parts of circles that are intersecting. All right, so my first one here, a tangent to a circle is perpendicular to, let me write it out, perpendicular to the radius drawn to the point of tangency. So a tangent to a circle is perpendicular to the radius drawn to the point of tangency. It's like a mouthful there. So what it means is where the radius and the tangent line intersect forms a right angle. Okay, so the radius and the tangent line, when they intersect, that forms a right angle. This comes up a lot. It's not angles that they mark because they just want you to recognize that a radius and a tangent line intersecting are perpendicular. Okay? All right. Next thing. Tangent segments to a circle from a point outside the circle are congruent. So congruent is your blank. So tangent segments to a circle from a point outside the circle are congruent. So these two tangent segments are coming from point N, right? So where they intersect the circle, those are both tangent lines, right? They only intersect in one spot. That means that these two parts here are going to be congruent. Two parts that are outside the circle coming from that point, that common point, they are congruent. So let's talk about why that is. Remember, I'm all about those connections. So let's switch back here for a second. So we just talked about how, in this case, angle A and angle G are congruent, right? They're actually right angles. Okay, well, what about AE and GE? What are those? They're congruent. Why? Because they are radii, correct? Okay, now, what if I were to draw in this segment, EN? If I could prove that top triangle congruent to the bottom triangle, then I could use CPCTC to say that AN and GN are congruent. Right? Okay, so I need another part. Same segment I heard, right? EN is congruent to itself. Okay, but I have an angle side side. Is that okay? It's really hypotenuse leg good because it's a right angle, right? So because it's a right angle, we have hypotenuse leg. So by CPCTC, then AN and GN are going to be congruent, which is what that last one was just talking about. So I'm trying to show you why that is. Does that make sense why they're congruent? Okay, now one more connection here. You just told me that AE and EG are congruent. So what shape do we have here? We have a kite. We've made a kite using tangent lines. Kind of cool, huh?
Crazy.
You didn't think those kites were going to come back. All right, so we've created a kite with our non-vertex angles being right angles. So keep in mind, how many degrees are there in every quadrilateral? 360. Because this is a kite made with tangent lines, these two angles have to be 90 and 90, right? Which means then there's only 180 degrees left for these two angles. So because it's a kite made with circles, or tangents, these two are going to be supplementary. So angle E and N have to be supplementary, because there's only 180 degrees left to work with all the time. Now, that being said, if I were to draw some random kite out here, these angles are still congruent, right? We're not guaranteeing that these are going to be supplementary. The only reason it happened is because those tangent lines of the radius formed right angles, and they're always going to form right angles. So that's not true for every single kite, only true for kites whose tangents make the kite with the radii. Does that make sense? Yeah? Okay. So, kind of cool that those are supplementary. There's also a formula that goes with this to find the measure of angle n. Okay? So if we want to find the measure of angle n, which is this angle outside, we have a special formula. I think this is way easier to think about because I can always draw in a kite. I can draw in my radii. But you also have the option of using this formula. I forgot my n equals here. Sorry. So the measure of angle n is equal to 1/2 of the major arc minus the minor arc. So where those tangent lines intersect, it really divides the arcs into two different regions. We have the major arc, which is the long way around, and the minor arc, which is the short way around. So, for example, if I gave you, let's say that this is 100 degrees. This minor arc is 100 degrees. Can we find the major arc then? Yep, how am I going to do it? 360 minus 100 would give me 260, right? Is that okay? All right, so now if I use my formula, I would have 1/2 of my major arc is 260 minus my minor arc, which is 100. So I really want 1/2 of 160, which is 80 degrees. Okay, so the math there is not difficult. But keep in mind, if I know this arc is 100 degrees, this central angle is also 100 degrees, right? I know G and A here have to be right angles, so then E and N have to be supplementary. So it's actually a little bit faster if you can think about it in terms of a kite. Even if your kite is not fully drawn in. Can I change off of this for a second? So what if I gave you, I'll just do that same problem. So here's my circle, and let's say they gave us two tangent lines. It's not going to be very accurate, but okay. So let's say they have two tangent lines like this, and they tell you that this is 100 degrees. The minor arc is 100 degrees again, and I want to find angle N. Okay, I don't have any radii drawn in, right? But it doesn't change the fact that I still have tangent lines. So you can literally just draw them in. So draw in your points to your point of tangency. I still know that's going to be a 90-degree angle, a 90-degree angle. My central angle then still has to be 100, and now I can work backwards to find that angle. So even if they don't draw those radii in for you, you can draw them in. Does that make sense? Because it doesn't change the fact that you have the tangent lines. All right. I have two slides next for you that just have some vocabulary. The first one are secants. So a secant is a line that intersects a circle twice. Okay, exactly 2 times. So a chord would stop at the circle. Right? A chord is a segment whose endpoints lie on the circle. A secant keeps going, either one way or the other or both. Right? So that's a secant. We're going to work with secants after break, but those also form angles outside of our circle. Then the last 2 terms came up on an SAT or an ACT question one time that a student asked me about. So I threw it in here just because I think once you see it, it makes sense. Okay. We don't really do anything beyond just introducing this, but circles can be tangent to each other. So we've talked about lines being tangent to a circle. The circles can be tangent to each other. So one way is called externally tangent circles. That just means the circles are outside each other and they're just intersecting in one exact spot. Like they're just barely touching each other. Okay? You can also have internally tangent circles. meaning one is nested inside the other, and they still just intersect in one spot. I think once you see it drawn out, like, again, we don't do anything with it, but it should make sense now. Is that okay? Again, just to introduce you to those terms. All right, I have 5 practice problems we're going to do. I want to do one of them together, and then I'm going to let you think through the last 4. All right, so this first one here says, find the perimeter of the triangle. So part of geometry is looking at figures in different ways. So we can see here that we have a circle inscribed in a triangle, right? The circle is inside or inscribed in the triangle. But you could also look at this as tangent lines to a circle. So what if I just focus on this? Let's do the right side here. So this angle right here is actually formed with tangent lines. If that's the case, then those 2 segments have to be congruent. Right? Because we know tangent segments that meet at a point outside the circle are congruent. That's true at every single vertex of my triangle. So the 9 here has to be congruent with this part. And the same is true with the 3rd vertex. These 2 sections here have to be congruent. It's about how you look at it. Yes, it's a circle inside a triangle, but those triangles are really tangents to the circle. Okay? So if this segment here is 7.7, this part has to be 7.7. Up top, if this is 9, this part here has to be 9. And then the bottom left corner, we can figure out. We know the whole left side is 15.4 units long. If the top part is 9, the bottom part has to be 15.4 minus 9, or 6.4, which means this part has to be 6.4. All right, so add them up. I believe you should get 46.2. 46.9. Okay, good job. Is that all right? All right, you try the next 4. You try the next 4.
It's okay. I actually sound it out. Right down. Also turns out parallel is not turns out
Would anyone like more time? We're all good? All right, for the next one, it's very similar to the one I did before, except now this is a circle inside a quadrilateral, right? Okay, so same ideas apply, that we have congruent tangent segments. Okay, so you're going to follow it around. If I know this whole side is 16, we have 8, this has to be 8. So now you can mark your congruent segments. Again, this bottom left side, the whole thing is 16. This part has to be 8 and 8. And then it actually ends up being 8 all the way around, right? Doesn't happen every time, but it does happen. Okay, so then your perimeter here is 64. So your answer is A. Questions on that one? All right, next one. Next one, we're going to solve for x. So this 28.9 is a distractor. Really, you need to know that your tangent segments are congruent, right? So those two expressions have to be equal to each other. So 9x minus 1 is equal to 7x plus 7. Subtract 7x from both sides, I get 2x. 2x, add 1, I get 8. Divide by 2, you get x equals 4. So the answer there is B. Is that one okay? All right, next one. I'll show you both ways on this one in terms of using a formula or drawing a kite. Okay, so for this one, if my major arc is 115, I'm sorry, my minor arc is 115. So my major arc has to be 360 minus 115, which is 245. Okay, so my formula is 1/2 of the major arc minus my minor arc. So I need 1/2 of 130, which is 65 degrees, right? Okay, the way I like to think about it, if I were to draw in these radii, even if it's not pretty, there's my right angles. If my arc is 115, so is my angle. Then my angle and angle T here, my central angle and angle T, have to be supplementary. So 180 minus 115 gives me 65. Again, both ways are correct. I think this is faster and easier. And if I start putting expressions in here, this is a little bit safer because it's easier to add these together to be 180. But when you start subtracting expressions, you have to make sure you distribute the negative. And you'll see that on your homework. Okay, that'll come up on your homework. All right, next one. Next one. On this one here, we're looking for angle F. I see my major arc is 255. So what does that make my minor arc? 105? Okay, so if I want to do my formula, I would have 1/2 of 255 minus 105. So 1/2 of 150. Sorry, I don't know why that took me right there. So half of 150 is 75. Is that okay? All right. I could have also just drawn in my radii. Again, if my arc is 105, my angle is 105. My central angle and angle F there have to be supplementary. So 180 minus 105 gives me 75. Is that okay? All right. So your homework is going to be a lot of problems like those, like a combination of those. I did keep it all multiple choice just to kind of keep the theme going today. Again, keeping it a little, I'm just trying to mix it up because I know how boring you the same people over over again. Okay. Okay, so tomorrow the plan is we're going to review, and then Thursday is quiz.
Well, let's go, baby. Turn me up, baby. I know.
I didn't feel bad.
All done? Thank you.
Everything.
So,